So the next topic what we are going to study is surface energy. Okay. See, many people are confused between surface tension and surface energy. Okay. But we here will try to establish a relationship between surface tension and surface energy, and how this surface tension, the liquid gets the property of minimizing its area, surface area. Okay. So now try to understand it. Again, it's a very interesting topic. Okay. Very interesting concept. See, you take a container. Okay. This is the surface of the container. I told you free surface matlab kya, which is free from shear. Inside whatever we call it bulk area. This is the surface area. Okay. Now take two molecules. One molecule on the surface. This molecule is surface molecule. This is your surface molecule. One molecule take inside, which we call it as what? Bulk molecule. What? Bulk. So what happens here is, to the bulk molecule, it will be equally stretched from all the sides. Okay, यहाँ से भी खींच रहे हैं. There also, there is cohesive forces. So throughout it has forces is being stretched to the which molecule? Bulk molecule. That's why what is the F net here? What is the net force? 0. What is the net force? 0 for the bulk molecule. Now what happens to the surface molecule? See, these molecules are pulling it downwards. Okay? But up, what is there? Above it, air. Air ka bhi itna, it's not that good enough. Adhesive force is not that strong enough between the surface and air to pull it the way the inside bulk molecules are doing. Okay, so that means here the molecules are pulling it downward. So the F net, the net force which is acting on a surface molecule is downward. The net force which is acting on the surface molecule is where? Downward. Okay, so I'll write here. So what is your F net? F net is downward. For which molecule? For the surface molecule. This implies, because they are pulling it downward, it will try to move downwards. The surface molecule will try to move downward. As they are trying to move downward, or they are coming downward to fill the empty space, what happens? The other molecules rise. Yes or no? In order to fill this, it has come down. So other molecules will try to go up. Isn't it? That means what? The liquid surface. That means the liquid surface is in continuous microscopic turbulence. That's why the liquid surface will be continuous microscopic turbulence. नीचे आ रहा है ऊपर. The liquid surface is coming down to fill the void. Other molecules are going up. The surface molecule is coming down. Other molecules are rising up and filling the void. That's why the liquid molecules are in continuous microscopic turbulence. Okay? But sir, you told F net of the bulk molecules are 0. So how they are going up? Unless they are doing some work. They have to do some work and go up. Isn't it? That means there has to be some work done. Against what? There has to be some work need to be done against the force of attraction of the molecules which are below the surface. This means work has to be done. Work has to be done against the force of attraction between molecules below the surface. How, sir? How they are doing? Which is stored? This work or nothing. This is stored in the form of potential energy, which is stored in the stored तो है, कुछ तो काम कर नहीं रहा. It's not flowing nowhere. It's a container, liquid is at rest, so it is stored. They stored in the form of which energy? Your potential energy, which is stored in the form of potential energy. Work you are doing, okay, against the force of attraction of the molecule below the surface, which is stored in the form of potential energy, and you are rising up. That means your liquid surface, always is having more energy rather than the bulk molecules. This implies liquid surface possess more energy than the bulk. That's why your surface of the liquid have more energy rather than compared to the rest of the liquid, or compared to the bulk of the liquid molecules. Understood? So that means what? Surface mein energy hai. You have more energy in the surface. See, keeping other aspects of this apart, your insects, some insects you will find they'll be walking on the liquid field, they'll be walking on the liquid surface. Why? Because your liquid has some energy to give them. It has some energy. Because of this energy, they utilize this energy. Obviously, they have some other biological factor also. The tiny insects, okay, you can find them walking on the surface of the liquid. Understood? We don't have that much. We will sink. Okay. So the liquid surface possesses more energy than the bulk. But what is the law of nature? Every molecule, everything in this universe tries to be as stable as possible. Correct? They want to be stable. The molecule wants to attain a stable state. In order to attain the stable state, what they have to do? They have to minimize the surface area. Dekha? है ना interesting? So, but lowest energy. See, they have to be in stable state. Stable state means they'll minimize the surface area. Why? Because they have to go for the lower energy level. They have to go for lower energy. Hence, what they will do? Minimize the surface area. They will minimize the surface area. What property is this? Minimizing the surface area? Yes. What property is this, sir? This property is nothing but surface tension. Now, surface tension and surface energy. You understood? You understood the relation between them? How did it come? Sir, please again, once you please make us understand. देखो, क्या हो रहा है? We have a bulk molecule. We have a surface molecule. Bulk molecule is being equally forced. The force is being acting on the bulk molecule equally throughout its periphery, throughout its circumference, from everywhere. It is being applied equal force. That's why the net force acting on the bulk molecule is 0. Wherever the surface molecule, which is the surface molecule, 1/2 is nothing. Okay, that's why only the force which are acting is downward only. That's why the net force is acting downward. Because the net force is acting downward, the molecule tries to come down. The molecule tries to sink. The molecule tries to come. When the molecule tries to come or it comes down, there is empty space or void present here. To fill this, the surrounding molecule will try to go there and occupy this position. Correct. So this continuously happens on the surface of the liquid. That's why the liquid surface is in continuous microscopic turbulence. बहुत छोटे से होता है. Okay. Because this liquid surface, these molecules to fill the empty space, they are coming up. That means they have to do some work. Okay, they have to do some work. How they will do the work if they don't have energy? They are doing some work because this is stored in the form of potential energy and they are coming up. So they have some extra energy. The surface of the liquid are having some extra energy compared to the bulk molecules. Okay, the liquid surface possesses more energy than the bulk molecule. But to come into a stable state, to come anything into a stable state, it should have a least energy. It should have what energy? Least energy to attain a stable state. So that's why what they will do, they will try to pull the molecules closer with the help of your cohesive force. Okay, and they will try to minimize the surface area. Why? They want to attain the lower energy state, right? They want to be stable. Stable means lower energy. Lower energy means they try to minimize the surface area by pulling the. Sir, समझ में नहीं आ रहा है. Surface में क्या हो रहा है? I'll draw the free body diagram of this surface. I'll draw the free body diagram of this surface. देखो, this, let's just say this surface is like this. Okay, ये surface. So the one molecule is here, one molecule is here, one molecule here. This molecule will be pulling each other. These two molecules will be pulling each other. These two molecules will be pulling each other. Similarly, these molecules will be pulling each other. So they will be pulling each other with the help of your which force? Cohesive force. Why? So they want to attain the stable state. In order to attain the stable state, they have to go to the least possible energy possible. In order to go to the least possible energy possible, then they try to stretch. They'll try to pull each other. They'll try to add cohesive force to each other, which helps in minimizing the surface area. Which helps in minimize the surface area. Which property helps in minimizing the surface area? What property we call it? We call it surface tension. We call it surface tension. So next time in interview somewhere, if they'll ask you the relation between surface energy and surface tension, you explain this pura. You explain them this entire thing. Okay, understood? Correct. Pause the video and note it down. Lick liya? So now, what we'll do is, okay, come on. Now we'll try to prove it little mathematically. We'll try to prove some mathematical thing of this. Okay, what is the surface energy? Okay, and how surface tension and surface energy are. Okay, related to आप समझ में आ गया, but how surface tension can also be written in terms of surface energy. ठीक है? Now, what you do is same. Take the U frame. Again, you take the U frame. ठीक है? This is the slider. This is the slider. Okay. You have some soap film here. You have already a soap film here. Let us say this distance being how much? X. Distance being X. The length of the slider is L. Length of the slider is L. So here they are applying forces which is taking it downward. Now you have to do some work against this force. So take the slider, move the slider slowly. कैसे? Slowly. Take the slider slowly towards this new position now. Take the slider to this new position now. What is the distance between this? Sir, delta x is the distance. What is the distance between them? Delta x is the distance. Okay. So what is the work you have done here? What is the formula? Or work done? Which force it acts? The force it is acting is F. You are doing the work against this force F, resistive force F. So what force you are applying this side? Here also F. F you are applying, but very slowly. But how you are taking? Very slowly you are taking this. Okay. So what is your work done? What is your work done? Delta W लिखता हूँ मैं और delta U. Okay, or you write delta W, no problem. Sir, the force, resistive force into the displacement. Resistive force into the displacement. Okay, what we have studied, sir, surface tension equal to force per length. So force equal to surface tension into length. So this implies this becomes sigma into L into delta x. One mistake I have done. What mistake I have done? I have not told you till now. There go. Whenever there is a soap film, okay, you can prove it, but you must know. Whenever there is soap film has two surfaces. Soap film has how many surfaces? Two surfaces. Suppose you have a soap bubble, okay. Inside the soap bubble, you have air. You have a soap bubble, okay. If you have a soap bubble, inside there is air, then the soap film, then again air. Okay, there is a surface between air and bubble. Second surface is between bubble and air. And when there is a soap film, thin soap film, there is also two surfaces. One inward, inside, one outside. And there is some gap between them, which is nearly zero. So this is your case 1, this is your case 2. In both the cases, your soap film or soap bubble has how many surfaces? 2. So whenever in question there is a soap bubble, soap film, anything related to soap, you must write here 2. Why? Because you have two surfaces. So 2 into sigma into L into del x. Can I write it like this? Sigma into 2L into del x. Sigma into 2L into del x. समझ में आ गया? Now, what was the initial area of this? What is the initial area of this, sir? Length L into x. What is now the final area? Hey, final area, sir, L, isn't it? Oh, 2 into L into x. Sir, 2 into L into x plus delta x. Now, what is your delta A? Final area minus initial area. कितना हो रहा है आपको? 2Lx cancel. 2L into delta x. 2L into delta x. That is the change in area. So, can I write sigma into delta A this? Can I write sigma into delta A? So, what became your surface tension? Sigma is also represented in terms of work done per unit area. So, the sigma can also be written, surface tension can also be written in terms of surface tension equal to work done per unit area. What is the unit of this work done? Sir, joule. What is this? Meter square. So, the surface tension is written as Newton per meter or joule per meter square. That is the amount of work you have done per unit area. Also signifies what? Signifies your surface tension. That is surface energy per unit area or the force per unit length. Which force? Which force? Cohesive force. Cohesive force. Cohesive force. Surface tension. Surface tension is mainly due to which force? Cohesive force. Cohesive force. The force of attraction between same molecules. Okay, molecules of the same component. Water, cohesive. Water, air, adhesive. Water, gas, adhesive. You understood? Water, air, glass, cohesive forces. Correct. And the surface tension is always present on the interface between two media. Interface. We need the interface to measure the surface. Sir, whatever you have drawn this. You have not told what is the interface. See, the interface is air here. Here is air. Here is your liquid. We need a interface. Otherwise, this is the interface. Otherwise, how am I going to make the surface? Need to space, vacuum, mudega. Matlab, it won't even. It will float. ठीक है? So we must need. Sir, if there are two liquids, suppose one is kerosene, one is water. तो kerosene का density तो कम है. It will come up. So that there also they will make a intersection, and the surface tension will find at the intersection only. Surface tension is always present on the intersection between two medias. So understood surface tension समझ में आया? You understood surface energy also? Come on. Yes. Pause the video and note it down. Pause. Now see, there is one more interesting thing. Okay. Now we will be studying what is the work done in converting a big liquid drop of radius r to n number of small liquid drops of radius small r. Okay. So we have a big liquid drop. What is the radius? What is the radius? Capital R. And we are converting it to small radius, small liquid drops of radius smaller. Okay, the radius is smaller. Radius is smaller. Radius is smaller. Okay, 1, 2, 3, dot, 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 up to n. Okay, all are having same radius, smaller. What is the radius of a big liquid drop? Capital R. Let us say the mass is here capital M, and here the masses are equal, small m. Okay, what we know? Mass is a unique quantity. Okay, mass is unique, so mass will be same. So capital M is nothing but n into your small m. N into small m. This implies capital M, sir, density into volume of capital M is equal to n into density into volume of these each water particles or water droplets. Okay, density is same, isn't it? They are also water, converting also water. So you cancel it. So what you got? Volume. So volume is becoming same. What is the volume of sphere? 4 by 3 pi r cube. N into here what? 4 by 3 pi small r cube. This implies 4 by 3 pi, 4 by 3 pi. Cancel. What you got? Sir, capital R cube is equal to N into small r cube. This is my small r cube equal to capital R cube by n, or small r equal to capital R by cube root of n. Small r equal to capital R by cube root of n. So what we are trying here is work done. What we formula में क्या पढ़ा? Sigma equal to the work done per unit change in area. Work done per unit change in area. So from this, what will be your work done? Sir, work done equal to surface tension into the change in area. So this implies sigma. Your work done equal to nothing but sigma into change in area, n into 4 pi r square minus 4 pi capital R square. This is the change in area, and this is the formula for work done in converting a big liquid drop of capital R to n number of small water drops. But sir, हम क्यों पढ़ रहे हैं? Why we are studying this? We will try to understand with the help of an example. Let us take the capital R be 8 centimeter. Okay, n be 64 centimeter. 64 numbers we are trying. So what will be your small r? Capital R by cube root of n. Capital R is 8 by 64 cube root. So 84 by 2. For how much? 2 centimeter is the small r. Okay. Now see the interesting thing. Calculate the area of the first droplet. 4 pi r square, the big drop. Total area 4 pi r square, that is 4 pi into r, 8 square, that is 4 pi into 64. Correct? Yes or no? Now see the small drops area, the cumulative area of all the small drops. How much? N into 4 pi r square. N is how much? 64 into 4 pi. R is how much? How much you got? 2 square. So what you got? Sir, we got 4 pi into 64 into 4. If you compare these two, what you are coming to know? How many times the surface area increased? 4 times. See, this is the beauty again. What you did is, now let us say, with this, using this area before, one person was washing its hand. Now you have used in your nozzle some drops. Okay, and you have converted a big drop into 60, big drop of 8 centimeter into a small 64 small number of droplets. So now with the same bucket of water, same mug of water, how many people can wash their hands? 4. Sprayer, your spray, DO what you take, okay, 1000 sprays they tell, yes or no? What will happen if you directly use the liquid? Obviously this volume is gonna be very, very less. Obviously its volume is gonna be, its area is gonna be very, very less. Correct. So that's why when you go for spray, more and more, this is just 64 I told. You can go for 6400 also. So more the surface area you increase, more the life you have increased, and you save the water. You can save more water, isn't it? So that's why I wanted to tell this. Okay. So our note it down. Pause the video and note it down. Clear? Okay. So the next topic is also interesting. So what happens is, be it is your water drop, be it is your soap bubble, be it is your liquid gel, they are having excess pressure inside them. They are having what? Excess pressure inside them. We are now going to calculate what is the excess pressure inside a water drop, what is the excess pressure inside a soap bubble, and what is the excess pressure inside a liquid jet. So excess pressure inside A. First we'll water drop. We'll study what is the excess pressure inside a water drop. Okay. So now this is your water drop. This is your water drop. Okay. What you have done is you have cut it into two halves. Okay. Two symmetry half. You take left side or right side, doesn't matter. You have cut it into two symmetric halves. Let me take the right side half. How it will look? Isn't it? It will look like a hemisphere. It will look like this. Correct. So because of this excess pressure, it is still bursting out. So the bursting forces are like this. Bursting forces. But normally it is in stable condition. Stable condition, that means some restoring forces are also acting. Where the restoring forces are acting? On the surface. That is your surface tension, surface force. This is your which force? Restoring force. This is your which force? Restoring force. Okay, bursting force and restoring force. So what is this bursting force, sir? Delta P into the area. Okay, what is this forces? Your restoring forces, sir, sigma into length. But in equilibrium, for equilibrium, your bursting force and restoring forces are same. So that means your delta P into the area. What is the area? Sir, pi by 4 d square is the area. Okay, is equal to, what is this? Sigma into L. L is acting on the circumference. On the circumference, let us say d is the dia of the drop. D is the diameter of the drop. Okay, and R is the radius, diameter of the drop. Okay. So sigma into L, where it is acting? Sir, it is acting on the surface. So surface tension pi into d of the perimeter of that. So this implies, what is your delta P? Sir, pi cancel, d cancel. What you got? Delta P is equal to 4 sigma by d. This is the excess pressure inside a liquid drop. Or if I write delta P is equal to 2 sigma by R. Delta P equal to 2 sigma by R. Delta P is the excess pressure inside a liquid drop. Delta P is the excess pressure inside a liquid drop. Now see this. ऐसे किया मैंने, ठीक है? This is inside. This is outside. Now see from inside. If you see from inside, this surface looks like how? Concave. This surface looks like concave. If you see outside, this looks like convex. This looks like what? Concave surface. From outside, if you see, it looks like concave, convex surface. Hence, the pressure inside the drop is always more, because excess pressure है ना. If here it is P naught, how much is here? Take 2 sigma by R. If outside the pressure is P naught, how much is on the concave surface? Concave surface it is P naught plus 2 sigma by R. So the pressure inside the drop is always more than the outside. That is, P concave is always greater than P convex. Remember this. So the concave side pressure is always and always more than the convex side pressure. So what is 2 sigma by R is the delta P. What is delta P? Sir, excess pressure. Excess pressure inside a liquid drop. Excess pressure inside a liquid drop. ठीक है? हो गया? Now we'll go for what? No, pause the video, note it down. Note it. So next we'll go for soap bubble. What I told you, how many surfaces are there in the soap bubble? Sir, 2 surfaces. One surface is inside. Inside there is a air which is stuck. There is a stuck or still air or the stuck air inside the soap bubble, and there is air outside the soap bubble. So there are 2 surfaces. One surface between the inside stuck air and the soap film. The other surface is the soap film and the outside air. So how many surfaces are there? There are total 2 surfaces. Okay. So next is your excess pressure inside a soap bubble. Excess pressure inside a soap bubble. Okay. Same thing. What you have to do? This is the soap bubble. Break it. If you break it, take one side of this, any side, left or right, you call it symmetric only. So I'll take like this. Okay. And there are how many surfaces? How many surfaces? 2 surfaces. What is this? Sir, bursting pressure because of the excess pressure inside, or we call it, it's going at what? Bursting forces. That is delta P into the area. Okay. Now what is here? Come on, sir. This is restoring forces. What is this? your restoring forces because of surface tension. Restoring forces. How many surfaces are there? 2. So 2 sigma into L. This is your restoring forces. Basically, how does it look? Come on. How does it look if I draw it here? देखो ऐसा है. One fill. There is other one like this. Let us say this radius be R and the thickness be how much? T. So now let me write for equilibrium. For equilibrium, your 2, that is delta P into area is nothing but 2 sigma into the length L. Delta P into area, what? Your pi r square is equal to 2 sigma L. What is L? Your 2 pi r plus this area, this circumference where it is acting, that is how much? 2 pi r into 2 pi into r plus t. But normally these two are so close to each other that we take t nearly 0. We take t nearly 0 because they are very close. So what you got? So delta p into pi r square is equal to 2 sigma into 4 pi r. 2 pi r plus 2 pi r. Okay, 4 pi r. This implies cancel. Pi you cancel. R you cancel. What you got? Delta p is equal to, no, if I am writing 2L here, sigma won't come. Sorry. Already I am writing now 2 surfaces I am writing, that's why I am not writing 2 here. Okay, that means if you will convert it, it's nothing but sigma into pi d you write now. This is nothing but sigma into 2 pi d. So that 2 will come here. That is 2 sigma pi d. Okay, or sigma pi d equal to 2r. 4. Okay, so what you got? Delta p equal to, come on, sigma, 4 sigma by r. Delta p equal to 4 sigma by r, or delta p equal to 8 sigma by d. That is the pressure, the excess pressure inside a soap bubble is nothing but 2 times the excess pressure inside a liquid drop. What was the excess pressure inside the liquid drop? 4 sigma by d. What is the excess pressure inside a soap bubble? 8 sigma by d. You understood now? You understood, or did I make you confused? Why this 2 is not here? Because already I am taking separately both. Okay, otherwise I would have written like this only directly. आ गया समझ में? So delta p equal to 4 sigma by r or 8 sigma by d. That is the excess pressure inside the soap bubble. Okay. Pause the video and note it down. Okay. So next we will be writing is the excess pressure inside a liquid jet. Liquid jet कैसे आता है? Cylindrical. Excess pressure inside a liquid jet. Next we will be writing is excess pressure inside a liquid jet. ठीक है? कितना repeat करोगे सर? Until you remember everything, I will repeat that time. Liquid jet. ठीक है? Let what is your length? L. The diameter be D. Diameter be D. So where the bursting pressure are acting? On this surface. Here you have nothing but bursting pressures are acting. Symmetry. Cut it from half and take it. How does it look? Sir, it will look something like this. Okay, so this is where your bursting forces are acting. So where the restoring force will act? Where the restoring force will act? Sir, along this periphery. That is the surface. यहाँ पर act करेगा your restoring force. Okay, restoring force, which is nothing but force because of surface tension. What is your delta P into area? what is your restoring force, sir? Force into length is nothing but your, sorry, sigma into length is nothing but your restoring force. Okay, now at equilibrium or for equilibrium, at equilibrium, your bursting force and restoring forces are has to be same. So delta P into area, what is the area? L into D, isn't it? What is the area? You have diameter D na, diameter D, length L. So this implies, what is this? Sigma into L, very what? 2 into L plus D. Normally what happens in a liquid jet? What happens in a liquid jet? The D is very less than L. So we can neglect the D here straight away. Okay. So what you will find here? Delta P is into L into D is equal to sigma into 2L. So L cancel. So what you got? Delta P? Delta P is nothing but 2 sigma by D. This is the excess pressure inside a liquid jet. Excess pressure inside a liquid jet. Now remember, what is the delta P for drop? See, question comes from here. That's why I am repeating so much. Delta P of drop is 4 sigma by D. What is the delta P of bubble? What is the delta P of bubble, sir? 8 sigma by D. What is the delta P of your jet? What is the delta P of the jet? That is 2 sigma by D. Okay. Pause the video, note it down. Very important. Questions comes from here. Excess pressure inside a soap bubble, excess pressure inside a liquid drop, excess pressure inside a jet. Jet nahi aata zyada. Mostly the question either will be from excess pressure inside a liquid drop or excess pressure inside a soap bubble. ठीक है? Note it down. Noted? Very good. Now the good. You have still left to here. You understood. So praise yourself. Come on. Tap on your back. You understood whatever we are trying to teach today. You understood all these things. Very good. Very good. Okay. So